Alright, so today's lesson is going to be about when we find those restricted values, what does that look like on a graph? So our main objective is to be able to determine the vertical and horizontal asymptotes and the holes that are in rational functions. And so these are the sub-objectives that we're going to be working on. Understanding the parent graph of a rational function, the transformations that happen, and then being able to identify the discontinuities of either holes or vertical asymptotes. Also talking about horizontal asymptotes and then putting that all together to write the domain and the range in both set and interval notation for these functions. And your essential question today is to be able to compare and contrast holes and asymptotes. So by the end of class, you should be able to take a function that's given, determine any holes, vertical or horizontal asymptotes, and then state the domain and the range of the function. So that's what we're going to be working up towards. So let's just do a quick refresher. We've talked mostly about three main graphs. We've also talked about exponential functions, but we're going to focus right now on linear, quadratic, and then absolute value parent graph. So see if you can sketch those in your notes. So pause the video right now and see if you can sketch or remember the graph of these three types of functions. So hopefully you were able to remember that a linear parent graph goes through 0, 0 and has a slope of 1. So that equation is just y equals x. The quadratic parent graph, y equals x squared. So it goes through the origin and then it goes over 1 up 1, over 2 up 4, and then it's also reflected over that y-axis. And then the parent graph of the absolute value is similar to the quadratic, only it has that slope of 1 and then it's reflected that slope of -1. So that's just a quick kind of refresher. And then if you'll remember, we take these parent graphs and then we apply different shifts. So they shift to the right, to the left, up, down, and what does that look like? So let's see how this impacts rational functions. So this is the equation of the parent function of a rational expression, so y equals 1 over x. What do you think the parent graph will look like? So I want you to use any means possible, maybe a table, maybe think about what's happening when I divide by x, things like that, and see if you can graph the function. Pause the video now. So when I went ahead and made a table, I wanted to see what's happening in the negative x values, what was happening at 0, and what was happening at the positive x values. So I went ahead and plugged in -3 for x, and I got -1/3, -2, so on and so forth. And these are the points that I ended up getting. So I can't really tell what's happening to the graph. So I'm going to find out what's happening between 0, because there was this weird error at 0. So I'm going to see what's happening between 0 and -1 and 0 and +1. So what I noticed is that as I got closer to that 0 value, it kept decreasing this way. So if I plug in -1/2, well, if I divide by -1/2, so I'm dividing by a fraction, so I'm actually going to multiply by the reciprocal. So I end up multiplying this one by the reciprocal of -1/2, which is -2, and 1 times -2 is -2. And so what I notice is that the closer I get to the 0 value, it's diverging down here, and then here it's going, it's increasing up. So I can see that the parent graph is going to have this kind of two-part to it, where it's going to look something like that, and obviously continue at those ends. All right, this is a really big concept in calculus when you get into your calculus class, is this idea of an asymptote. And we've talked a little bit about an asymptote in the past. We've talked about it's a vertical or horizontal line where the as the values get closer and closer to it, but they never touch it. So that's what's happening right here, is I can keep plugging in bigger and bigger and bigger numbers for x. So I can go all the way out to 100 and 200 and 300, but all I'm doing is I'm ending up dividing by that value. So it's going to get closer and closer and closer to 0. That y value, or the output's going to get closer and closer to 0, but it's never going to touch 0. There's always going to be just a little bit of a fraction. So if I plugged in 1,000,000 for x, it would be 1 divided by 1,000,000, which is going to be a really, really, really small number, but it's still not going to be quite 0. So there is actually a horizontal asymptote, so right here, on the x-axis. So the parent graph has a horizontal asymptote at the x-axis, or when y equals 0. And likewise, if you notice, we didn't really know what was happening between 0 and -1 and 0 and 1. And so I plugged in some fractions, and what I noticed is the closer I get to this y-axis, it's going to get larger and larger and larger, because the opposite of this is happening. When I divide by a really teeny tiny fraction, that's the same as multiplying by the reciprocal, so the output's going to be a really big number. So if you notice, there's actually going to be, since 0, I can't divide by 0, so x can't be 0, which is the y-axis, it's going to get closer and closer and closer to that value, but it's never going to touch it. So of the parent function, there's also a vertical asymptote on the y-axis, or when x equals 0. So we're going to talk more about that, but I just wanted you to kind of get a general idea of what the parent graph looks like for a rational function. So on this part, I want you to use your prior knowledge when we've talked about quadratic functions, those parent graphs, in the vertex form, and how we shifted things. Remember, if we added or subtracted inside the parentheses versus outside, how it shifted it left, right, up, down, and your knowledge of absolute value. We also did those functions when it was inside the absolute value bars versus outside. So I want you to do some predictions. Each one of these has the parent function, so 1 over x, but there's been some different transformations that have happened. So go ahead and predict what's going to happen to each of these. Pause the video now. Alright, so if you recall, when I add or subtract on the outside of that function, so onto the end, it's going to shift it up or down. Subtraction shifts it down, addition shifts it up. So in this case, this graph is going to shift down 3. And if you recall, when we added or subtracted inside of the parentheses when we were squaring, or inside of the absolute value bars, it shifted the function left or right. And remember, it always did the opposite of what we thought. Normally when we see plus, we think to the right and negative to the left, but it's going to do the opposite. So this one is actually going to shift left 3, and then this one's going to shift right 3. When I have increased my numerator, so I'm doing 3 divided by x, it's going to have a vertical stretch of 3, and then that negative is going to reflect the whole graph over the x-axis. So if you noticed, on the parent graph, there were 2 parts to it, quadrant 1 and quadrant 3, so it's going to reflect those to quadrant 2 and quadrant 4. So I want you to look over the next 3 graphs, and this is just a visual of what we just talked about. And I want you to analyze what's happening and how does that impact affect the parent graph. So in each one of these examples, the parent graph is the bold line. So the y equals 1 over x in each one of these. What happens? So hopefully you noticed that, like we talked about, when I increase the a value, so that value that's in the numerator, it's going to cause vertical stretch. So now instead of going to 1, 1, it's going to be at 1, 2, or it's going to be at 1, 3. Likewise, in the negative direction, it does that as well. Like we talked about, when I multiply a by a -1, it's going to reflect it over the x-axis. So what was above the x-axis is now below, and what was below is now above. And then adding on to the denominator is going to cause a horizontal shift left. All right, look over these transformations and see if you can come up with a generalization. So hopefully you notice that when I subtract in the denominator, it's going to cause a horizontal shift to the right. And when I add onto the end of the parent graph, so 1 over x, and then add or subtract something, that's going to cause a vertical shift up. And subtracting is going to cause that vertical shift down. So I want to revisit when we talked about the parent graph in general, and we talked about those vertical asymptotes and the horizontal asymptotes. So the parent graph always has a horizontal asymptote at y equals 0 and a vertical asymptote at x equals 0, so on the x and y axis. So I want you to keep that in mind, and we're going to go back and look at these graphs that we just talked about, and we're going to talk about the domain and the range. So if I were to write the domain of this, the parent graph, so I know that it's going to, the x values, I can put in any x value except for when I put in 0, I get an error. So that means I'm going to have all x values except for 0. So we're going to practice writing in both the set and the interval notation because you're going to need to know both. So just as a refresher, the set notation is going to be all values of x such that x cannot equal 0. So it's all real numbers except for 0. Or I can write it in that interval notation of negative infinity to 0, that interval, unioned with 0 to positive infinity. So just showing that there's this slight little break right between, or right there at 0. So the range is going to be, so the range also has that 0. We're talking about the y values now. So all the y values exist on this graph except for when y equals 0. So all y is such that y cannot be 0, or in interval notation, it's going to be the interval from negative infinity to 0, and then it's going to jump over and it's go from 0 to infinity. So those are the domain and the ranges, the ways we're going to write it for these rational functions. All right, so if I have to write the domain and the range of a given function, I need to think about those transformations that have happened. So we're going to go back to 3 of the examples that we had before and 2 new ones, which is a composition. So shifting left 2 and down 4, shifting right 6 and up 1. So I need to write the domain and the range. So remember that the parent graph, that 1 over x, is going to always have an asymptote at y equals 0 and x equals 0. So we're going to think about, what does this shift do? What does this transformation do? So I like to just sketch a graph of the function. So when I think about taking the parent graph, which would normally be in quadrant 1 and quadrant 3, and I'm shifting it down 3. So I'm now taking that that horizontal asymptote, and I'm shifting it down to where y is negative 3. So now I've got this graph that comes down to negative 3 and starts at negative 3 and goes down. So now I'm going to write my domain and my range from there. So for writing the domain, the graph only shifted up or down. So the only thing that's going to change is that range value. So the domain still has that asymptote at 0 because it didn't shift left or right any. So the domain will be the same as the parent graph. All x's such that x cannot equal 0, or it'll go from negative infinity to 0, union with the interval from 0 to infinity. So go ahead and see if you can pause the video and try to write the range. So hopefully you're able to realize that the graph just shifted down 3. So instead of being all values except for 0, it's all y values except for negative 3. So that would put the interval going from negative infinity to negative 3, and then jumping over that line and starting at negative 3 and going to positive infinity. So go ahead and pause the video and see if you can write the domain and the range for the remaining 4 problems. I'd like you to try at least one of them in both notations. Alright, so let's see if I did this correctly. So this graph right here, we know because the denominator is adding 3, it's going to shift left 3. So the only thing that's changing is the x values if it's shifting left or right. So the range is going to stay the same. It's going to have that asymptote at y equals 0. So it's all y values except for where y is 0, or the interval from negative infinity to 0 with the with the interval of 0 to infinity. But the x values, or the domain, did shift to the left 3. And remember, x cannot be negative 3 because then I would be dividing by 0. And that's why that's that negative 3. And so that domain value in both set and interval notation. So down here, this graph right here is going to shift right 3 because my denominator is x minus 3. So again, the range is not going to change when I'm shifting left or right, just the domain. So the domain values are now all values of x except for 3. And then the range is going to be where y cannot be 0. So this is a combination, and it's going to be a graph that shifts left 2 and down 4. So that's going to affect both the domain and the range. So my parent graph is going to shift left 2, and it's going to shift down 4. So now this is my domain restriction, would be the -2, and my range restriction is going to be -4. So my asymptotes are going to be right there. That's both inset and interval notation. And then this one is going to shift right 6 and up 1. So that's going to affect both the domain and the range. So this would be the right 6, all x values except for x is 6. And then up 1 is going to be all y values such that y does not equal 1. So go ahead and write down any notes or questions or anything that you want to bring up when we talk about this tomorrow. All right, this next one, it's asking you to write the equation g of x. So we're showing a new function that represents the transformation of this function right here. So given that f of x is 3 over x, I need to write a function g of x that shows a vertical shift down 2 and a horizontal shift right 3. So go ahead and pause the video and see if you can write that function g of x. So your function should be g of x equals 3 over, because that part's not changing, a vertical shift down 2 would be subtracting on the end 2, and then a horizontal shift right 3 is going to be x minus 3. All right, go ahead and pause the video and try the 3 remaining problems. All right, so assuming I didn't make any mistakes, you should have found that in this case, if I go up 4, that's going to be a +4 on the end, and a horizontal shift left 1 is going to be a +1 in the denominator. Down here, a left 2 is going to be a +2 in the denominator, and then shift down 1 would be -1 on the end, and right 2 would be a -2 in the denominator. Go ahead and make note of any questions or points of confusion that you have. All right, so we are done with the first portion of the notes. So go ahead and kind of write yourself, have some sort of interaction, some sort of B2 statement. What are you going to need to remember about this section of the notes? Go ahead and pause the video and write that down. All right, so right now I want you to go back to the very beginning of this module, and I want you to simplify this fraction, 2x squared plus 8x over x squared plus 7x plus 12, and I want you to identify the discontinuity. So where are there values of x that they can't exist? So where is the graph not continuous, essentially, and why? So go ahead and pause the video and simplify this function. So we're going to have two types of discontinuities. I want you to hold on to that function that you just simplified, and we're going to come back to it. But there are two types of discontinuities. We have a hole, which is just a single point where the graph has no value, or we have an asymptote, which is an entire line that the graph approaches but never touches. So if you look in this drawing right here, you can see I have a horizontal asymptote at y equals 1. And I have a vertical asymptote at x equals 1. And it's where that graph continues in its same pattern, but it just never touches that. Whereas a hole, this right here at -1, 2 is a hole. So it's a value, so x cannot be -1. It just jumps right over that. It continues in its pattern, but there's just a hole there. So we're going to talk about when do I have holes and when do I have asymptotes. So we're going to start with a horizontal asymptote. So we're using the same function as we work through all of these different discontinuities. So a horizontal asymptote is when the highest degree, that's what determines the horizontal asymptote. So I look at the highest degree in both the numerator and the denominator. So when I look at the numerator, my highest exponent is squared, and in the denominator, it's also squared. So I find the highest degree in both the numerator and the denominator, and then these are the three different situations I have. If the degree is larger in the numerator, so in this case, I have a degree of 2 and a degree of 2. So if the degree is larger in the numerator, then there won't be a horizontal asymptote. Well, 2 and 2 are the same value. So if the degree is the same in both the numerator and the denominator, then the coefficients make the horizontal asymptote. So a horizontal asymptote is where y equals. So my asymptote is going to be at y equals, and I just use the coefficients. So the coefficient of the degree of 2 here is 2, over, and the coefficient of the degree of 2 here is a 1. So 2 over 1, or just 2. So this is a graph that has been shifted up 2 because of that horizontal asymptote. And then if the degree is larger in the denominator, so if I had a to the third power here, then the horizontal asymptote is just on the x-axis. So that would be where there is no shift up or down. And we'll do some more examples with this. So other discontinuities that can happen are I can have holes or vertical asymptotes. So hopefully in this previous example, you were able to factor the numerator to 2x times x plus 4 and factor the denominator to x plus 4, x plus 3, and recognize that before I ever cancel anything, x cannot be negative 4 and x cannot be negative 3. So those are my restricted values. So we know that there are two discontinuities where x is negative 4 and x is negative 3. So we're going to get these definitions. A hole is where the discontinuity that cancels out, and a vertical asymptote occurs at the discontinuity that remains. So when I look at this problem, I notice that x plus 4 and x plus 4 are going to cancel. So this discontinuity of negative 4 is going to be just a hole. It's not going to be an entire vertical line. There's going to be a hole where x equals negative 4. And then an asymptote, a vertical asymptote, occurs at the discontinuity that remains. So there is nothing that will cancel with x plus 3. So my final answer to this simplified would be, of course, 2x over x plus 3. And since that x plus 3 remained, I'm going to have a vertical asymptote at x equals negative 3. So that's the difference between a hole and a vertical asymptote, is which one cancels and which one remains. Alright, so let's put this whole example together. So we found that there was a horizontal asymptote at y equals 2 because we looked at the largest degree in the numerator and the denominator. We saw where they were the same, so their coefficients formed that horizontal asymptote. We knew there was a hole at negative 4, x equals negative 4, because that was a discontinuity that canceled out. And then we knew there was a vertical asymptote at x equals negative 3 because that was the discontinuity that remained. So once I've identified all of those, I want to write out the domain in both set and interval notation. So go ahead and pause the video and see if you can think about domain being the x values and write it in both set and interval notation. Alright, so you should have recognized that we're talking about x values if we're talking about the domain. So there were discontinuities at x is negative 4 and negative 3. So the domain is going to be all x values such that x cannot be negative 4 or negative 3, which would put in interval notation from negative infinity to negative 4, that interval, negative 4 to negative 3 interval, and then negative 3 to infinity, and I'm going to union those together. Alright, so what I'd like you to do is pause the video, and I'd like you to try number 2. So find and describe the points of discontinuity for the given equation, and then state the domain and range of the function. So I want you to find any vertical, horizontal asymptotes, any holes, and then just state the domain of the function. See what you can do. Alright, so if I did this right, I found that there was a horizontal asymptote on the x-axis, because when I looked at the largest degree of both the numerator and the denominator, the degree is larger in the denominator because I have a to the third versus to the second. So by rule, the horizontal asymptote is the x-axis, or where y equals 0. Alright, when I factored it, I ended up, my completely factored form, I ended up with 9x times 3x plus 8 over 27x times x minus 2 times x plus 1. So nothing canceled, none of my restrictions canceled, so that's why I had no holes, which leaves my x equals 0, x equals 2, and x equals negative 1 to be my vertical asymptotes. So there are vertical asymptotes at x equals negative 1, 0, and 2. And the domain, I can either write it in set notation or in interval notation. So make sure you write down any questions or points of confusion that you have, and we'll talk about it tomorrow. Alright, so same thing here. I'd like you to pause the video and see how you can do with finding those holes, asymptotes, and then the domain, just the domain of the function. Alright, so hopefully you were able to figure out that when I look at the original problem, I have the largest degree on both the top and the bottom are equal. So I take the coefficients 2 over 1, and that gives me my horizontal asymptote of y equals 2. Once I factor it, I ended up with x cannot be negative 2 or negative 3. But the negative 3 is the one that cancels, so that becomes a whole. And then what remains is my vertical asymptote. So when I put my domain together, I have all x's such that x cannot be the whole, negative 3, or the vertical asymptote of negative 2. And this was what that would look like in interval notation. You can use either one unless it tells you specifically which one to use. And go ahead and write down any questions or point of confusion that you might want to talk about tomorrow in class. Alright, pause the video, try this one. Alright, so when I worked this out, I ended up with no horizontal asymptote, no holes. I had vertical asymptotes at x equals negative 3 and then over at x equals 3, which put my domain at all x's such that x does not equal negative 3, or in interval notation it would look like that. So if you got those answers, go ahead and move on to example 5. If you didn't, I'll just explain it right here. So for the horizontal asymptote, I look at the largest degree in the numerator and the largest degree in the denominator, and I see that the higher degree is in the numerator. And according to our rule is if the higher degree is in the numerator, then there is no horizontal asymptote. So then I factored, and this was kind of a double factor. I took out an x, which left me with x squared minus 1, which can be factored as x plus 1, x minus 1, because that's a difference of squares. And then over here, I took out a 4, and I was left with x squared minus 9, which I also recognized was a difference of squares, so x plus 3, x minus 3. So that gave me x values that could not be negative 3 or 3. And nothing canceled, so that's why there were no holes. Both of those discontinuities became vertical asymptotes, and then I just wrote my domain from there. So if you have any questions or points of confusion, make sure you write them down here, and we'll talk about them tomorrow. Alright, go ahead and find and describe the points of discontinuity, and then find the domain of the function. Alright, so when I factored this out and worked through this problem, first I started with my horizontal asymptote at negative 2, y equals negative 2. I found two holes at x equals negative 4 and 0, and then I found a horizontal asymptote at x equals 3, which put, with those restrictions, my domain being all x's, such that x is not negative 4, 0, or 3, and then that is the interval notation of it. So if you got that, you can go ahead and skip to our final problem. And if not, I'll explain it here. Alright, so as far as the horizontal asymptote, I find my highest degree in the numerator and my highest degree in the denominator, and they are the same. So my horizontal asymptote just becomes the coefficients reduced. So the coefficient of the numerator is negative 2, the coefficient of the denominator is 1, so that puts a horizontal asymptote at y equals negative 2. When I factored this out, in the numerator, ended up with negative 2x, and that left me with x plus 4. And then in the denominator, I took out an x, which left me with this trinomial, and I could factor that trinomial further. So I ended up with negative 2x squared, x plus 4 in the numerator, and then x times x plus 4, x minus 3 in the denominator. So that left me with 3 discontinuities in this function. X is 0, cannot be 0, negative 4, or 3. And when I went to simplify, the x plus 4 is canceled, so that made negative 4 a whole. But also, there were 2 x's on the top and 1 on the bottom, so the x equals 0 also canceled. So that's why there's a hole there. And then what remained was the x minus 3, so that meant that the x equals 3 restriction became a horizontal asymptote. And then those numbers together just became the domain. So if you have any questions or points of confusion, please make sure to write those down now, and we'll talk about them tomorrow. Alright, final example. Go ahead and pause the video and see how you do. Alright, so for horizontal asymptotes, I got y equals 1/3. For holes, I got x equals 4. For vertical asymptotes, I got x equals 0, and then the domain would be all x's such that x cannot be 0 or 4, or this would be it in interval notation. So if you got that, go ahead and skip to the end of the, to the next slide. If not, I'll explain it now. So my horizontal asymptote comes from the highest degree in the numerator and the denominator, which is both 2. And so the coefficients become the horizontal asymptote since they're equal. So it's 1 in the numerator and 3 in the denominator. So that's why it's 1/3. When I factored it out, this is what I got. So I set my restricted values to be x cannot be 0 and x cannot be 4. And when I went ahead and factored and canceled the x minus 4, or the x value that cannot be 0, that discontinuity became a whole because it factored out, which left the vertical asymptote to be x equals 0 because that one remained. And then my domain and range came from there. So if you're confused on any of this or have questions, please make sure you write those down and we'll talk about it tomorrow in class. So we've now met all parts of our objective. You can find the vertical and horizontal asymptotes and the wholes in a rational function, as well as writing the domain and the range given specific situations. So I'd like you to write down what are 3 errors you think students tend to make when determining the discontinuities of a rational function. What makes sense to you? What's your summary? What are things you need to remember? And then what are your be sure to statements about this lesson? So take a look at the different pieces. Where were you making mistakes? Where were you a little confused? And make sure you write those down.